So in the previous video, in the first video, we covered the normal distribution, in the second the binomial distribution, and now the hypothesis testing for the Poisson distribution. So again over here the testing is for the mean or the average, that is the value of lambda. So h0 will be lambda equals to a certain value, and then the alternative hypothesis will be h1 that is greater than the certain value, less than it, or not equal to it, same as the normal distribution and the binomial distribution, that is one tail, two tail. So I'll just write the examples of it. h0 will always be lambda equals, let's say, lambda naught. h1 can be lambda greater than lambda naught, lambda less than lambda naught, and lambda not equal to lambda naught, in which these two are one tail, this is two tail, this is upper tail, this is lower tail. The rest of the working is pretty simple. I think let's just go to the questions to explain it. So cloth made at a certain factory has been found to have an average of 0.1 falls per square meter. Suki claims that the cloth made by her machine contains on average 0.1 falls per square meter. In a random sample of 5 meters square of cloth from Suki's machine, it was found that there were 2 falls. Assuming that the number of falls per square meter have Poisson distribution, state the null and alternative hypothesis for a test of Suki's claim. So 0.1 falls were per square meter, but Suki was taking a random sample of 5 meters square. So that will be 0.1 times 5, that is 0.5. So h0 will be lambda equals to 0.1 times 5, that is lambda equals to 0.5, and h1 will be, Suki claims that the cloth made by her machine contains on average more than 0.1 falls, so lambda is greater than 0.5. This is the alternative hypothesis. So that's the first part. The second part, test at the 10% significance level whether Suki's claim is justified. So let's say that the number of falls is the random variable x. It follows Poisson with average 0.5, right? So we know that the significance level is 10%, and it is an upper tail test because it's greater than the alternative hypothesis. So this means that the extreme right values, the probabilities of the extreme right values should add up to 0.1. So let's take probability of x greater than or equal to, let's try 2. So that will be equal to 1 minus probability of x less than or equal to 1. So 1 minus, for Poisson the probability will be e power negative 0.5, 0.5 power 0 upon 0 factorial minus e power negative 0.5 times 0.5 power 1 upon 1 factorial. So this will be 1 minus e power negative 0.5, 1 plus, this is equal to 0.09. So probability of x greater than equals to 2 is 0.09. So probability of x greater than equal to 1 will be 1 minus probability of x equals 0, that is 1 minus probability of x equals 0 is e power negative 0.5, that is 0.393. Since this is more than 0.1, so we'll be rejecting this. So the rejection region, that is the region with 0.1 probability, is x greater than equals to 2, and the acceptance is x equals to 0 or 1. Now over here she gets 2 false, so that means that it will be rejected. So Suki's claim is correct that the average is greater than 0.5. Since the null hypothesis is being rejected, so the alternative hypothesis will be accepted. Then in the past, number of cars sold per day at a showroom has been modeled by a random variable with distribution Poisson 0.7. Following an advertising campaign, it is hoped that the mean number of sales per day will increase. In order to test at 10% significant level whether this is the case, the total number of sales during the first 5 days after the campaign is noted. You should assume that a Poisson model is still appropriate. Given that the total number of cars sold during the 5 days is 5, carry out the test. So firstly, H0 will be lambda equals, so it's 0.7 per day times 5 as we're taking a 5-day sample, that's 3.5. And then for H1 there are more sales, so lambda is greater than 3.5. Right, now it's a 10% significance level and it's again an upper tail test similar to the last question. So let's take probability of x greater than or equals to 1. If this is less than or equal to 0.1, then we will take this as the critical or rejection region. So for x is greater than or equals to 1, we'll have 1 minus probability of x equals 0. That is 1 minus e power negative 3.5. This is 0.9698. This is a big value. So probability of, let's see, x greater than or equals to 3. So that will be 1 minus probability of x less than or equal to 2. So 1 minus 0.494. This is again wrong because it's more than 0.1. So let's try x is greater than or equals to 5. It will be 1 minus probability of x less than or equal to 4. This is coming equal to 0.274. Again, this is bigger, so probability of x is greater than or equals to 6. Will be 1 minus probability of x less than or equal to 5. This will be 0.142. Probability of x greater than or equals to 7 will be 0.0652. So this is the correct region. So rejection will be x is greater than or equals to 7. Since over here the cars sold are 5 in 5 days, so that will, the rejection region is greater than 7. So 5 is in the acceptance region, so we accept H0 and the claim is not justified. So there is no evidence that the sales have increased. Then in the second part, the number of cars sold per day at another showroom has the independent distribution Poisson 0.6. Assume the distribution for the first showroom is still Poisson 0.7. Find the probability that the total number of cars sold in the two showrooms during the 3 days is exactly 2. So 2, we combine these distributions to get the total number of cars. So expected values will be added, 0.7 plus 0.6, 1.3, and variances will also be added. So again 0.7 plus 0.6 is 1.3. So it still follows Poisson with 1.3. So I'll just do it above. So during the 3 days there have to be 2 cars, right? So this was for per day, so lambda will be 1.3 times 3, that is 3.9, and then probability of x plus y equals to 2, so that is equal to e power negative 3.9 power 2 upon 2 factorial. This is equal to 0.154. Okay, so the next question again, as in binomial, we did in binomial. First we did some basic questions, then we did approximation to normal. So again over here this is approximation to normal. So flies stick to wet paint at random points. The average number of flies is 2 per square meter. A wall with area 22 meters square is painted with a new type of paint which the manufacturer claims is fly repellent. It is found that 27 flies stick to this wall. This is suitable approximation to test the manufacturer's claim at the 1% significance level. Take the null hypothesis to be mu equals to 44, where mu is the population mean. So mu is the population mean, right? The average number of flies is 22 square meters, and okay. So basically, first H0 and H1. So for H0, what we did was that it was the average number was 2 per square meter, and then there was 22 meters square, right? So the average will be 2 times 22, that is 44, or you can write it as mean as well. And then H1 will be is fly repellent, so it should be lesser than, or you can write mu is less than 44, right? So since lambda is greater than 15, so over here we can approximate to the to the normal distribution. So x follows normal with mean as 44 and variance as well as 44. Now we have to find if there are 27 flies stick to this wall, to find if they follow the, if they are, what's the hypothesis, how are we testing the hypothesis, right? So I'll just draw a graph first. The mean is 44 and we have to test for 27. So let's say 27 was over here. It's a lower tail test, right? So we need to see what is the probability before 27, right? So probability of x less than 27. Now over here we went from a continuous to less than equals 27, from a discrete to a continuous distribution, so we'll have to apply continuity correction. So z is less than or equals to 27.5 minus 44 upon root of 44. This is equal to probability of z less than or equals to minus 2.487. 1 minus phi of 2.487. So from the z table phi of 2.487, phi of 2.487, 0.9935. So 1 minus 0.9935, 0.0065. So that means that this region, the area of this region is 0.0065, whereas the critical region, whereas the rejection region has an area of 0.01. So that means that 27 lies within the rejection region. So H naught will be rejected, and the claim of the manufacturer is supported. I hope this is clear. So next is the errors in a Poisson in the hypothesis testing of a Poisson distribution. So again, the errors are the same as in the binomial and normal, that is type 1 and type 2 errors, and it's the similar kind of working. So let's just go to the questions. The first question is, the number of severe floods per year in a certain country over the last 100 years has followed a Poisson distribution with mean 1.8. Scientists suspect the global warming has now increased the mean. A hypothesis test at the 5% significance level is to be carried out to test the suspicion. The number of severe floods X that occur next year will be used for the test. Sure, the rejection region for the test is X greater than 4. Right, so first part, H naught is lambda equals 1.8, H1 is lambda greater than 1.8. So X follows Poisson 1.8. X follows Poisson 1.8, right? So they're saying that sure, the rejection region for the test is X greater than 4. So let's find probability of X greater than 3. So it's a upper tail test. So greater than 3, probability of X greater than 4, and probability of X greater than 5. The one that is slightly less than 0.05 will be the correct one. So for X greater than 3, it's going to be 1 minus probability of X less than or equal to 3, 1 minus probability of X less than or equal to 4, probability of X less than or equal to 5. Zero point 109. Zero point 0364 and this is 0.0104. So we needed 0.05%. X greater than 3 is more than that, so this is wrong. X greater than 4 is correct. It falls inside the range. This is less than X greater than 4, so this will also be rejected. So it has to be X greater than 4. Part 2. Find the probability of making a type 2 error if the mean number of severe floods is now actually 2.3. Okay, so the rejection region was greater than 4, X greater than 4. The acceptance region was 0, 1, 2, 3. So you have to find the probability of, so now basically X follows Poisson with 2.3, and we have to find the probability of the acceptance region for the wrong null hypothesis using the new null hypothesis. So probability of X less than or equal to 3 is equals to e power negative 2.3, 1 plus 2.3 plus 2.3 square upon 2 plus 2.3 cube upon 3 factorial. So this will be so e power negative 2.3 this is 0.799. So over here one mistake I made is that this was x greater than 4, so we'll also include 4 over here. So this will be plus 2.3 power 4 upon 4 factorial. So this will be 0.916. I hope this question is clear. Next question, the number of sightings of a golden eagle at a certain location has a Poisson distribution with mean 2.5 per week. Drilling for oil is started nearby. A naturalist wishes to test at the 5% significance level whether there are fewer sightings. He notes that during the following 3 weeks, there are 2 sightings. Find the critical region for the test and carry out the test. Right, so H0 and H1. So it's for 3 weeks. The test is being done for 3 weeks. So we'll multiply 2.5 with 3, that is 7.5. And then it's saying that lambda decreases, so less than 7.5 and H1. So X follows Poisson with 7.5 to find the critical region. That is the rejection region. So over here it's a lower tail test. So we have to find the lower values whose probabilities add up to 0.05. So probability of X less than or equal to 2. This will be 0.02. Probability of X less than or equal to 3. 0.059. Since this is more than 0.05, this will be rejected, and this will be the right critical region. So critical region is 0, 1, 2, and what are the sightings? There are 2 sightings in 3 weeks. So since 2 is in the critical region, so reject H0, and the naturalist suspicion proves to be right. As there are fewer sightings, as lambda is less than 7.5 is accepted. So there will be fewer sightings. So that was the first part. Second part, state the probability of a type 1 error. So type 1 error probability will be the probability of, because rejection is from x less than or equal to 2, that will be 0.02 or 0.202, 0.0202, 0.02026, 0.0203. This, and then third part, should why the naturalist could not have made a type 2 error. H0 was not accepted. Whether it be true or false, H0 was not accepted, and type 2 is the false H0 is being accepted. So since there is no H0 accepted, type 2 cannot occur. This was the last question. I hope it made sense. So we've completed the syllabus for hypothesis testing. We've covered all of the points in these 3 videos. I hope it made sense.